Welcome back. In the previous lecture, we have recovered molecular partition function from the more general canonical partition function. We discussed that how to connect these two partition functions for distinguishable molecules and for indistinguishable molecules. We also discussed conditions that when the molecules can become distinguishable. And then we were trying to connect internal energy with molecular partition function. First we talked about distinguishable molecules, and it turned out that for distinguishable molecules the expression for internal energy is the same that we had earlier derived when we were connecting internal energy with molecular partition function. Now let us discuss that if instead of distinguishable, if the molecules are indistinguishable, then what happens? Now let us talk for indistinguishable molecules. Indistinguishable molecules. If indistinguishable, then Q is equal to Q raised to the power n over n factorial. That 1 over n factorial is required. Alright. Now let us see what happens. U minus U0 from this expression is minus 1 by Q. That means minus n factorial over Q raised to the power n, that is minus n by Q, minus 1 by Q into derivative of Q raised to the power n over n factorial with respect to beta at constant volume. In other words, now what I have, U minus U0 is minus n factorial over Q raised to the power n. 1 by n factorial will come out from here, and then I will have n into Q raised to the power n minus 1 into del Q del beta at constant volume. This is what I have. N factorial cancel, and what I will have now, U minus U0 is equal to minus n by Q into del Q del beta at constant volume, because this Q raised to power n minus 1 is there, which is Q raised to the power n divided by Q. So Qn will get cancelled, and I will have minus n by Q del beta at constant volume. Interesting result to be now noted. Even for indistinguishable molecules, the internal energy is still, in terms of molecular partition function, the same as we got for distinguishable molecules. Right? We have the same expression, U is equal to U0 minus n by Q del Q by del beta at constant volume, which in other words, in terms of logarithmic terms also you can express, which is minus n del log Q by del beta at constant volume. That means we have now shown that whether the molecule is distinguishable or indistinguishable, you can use the same expression in terms of molecular partition function. Right? So same expression for distinguishable, that is Q equal to molecular partition function raised to the power n, or indistinguishable, Q is equal to Q raised to the power n over n factorial. The expression turns out to be same. So what are the points to be noted? That first we need to identify whether the molecules are distinguishable or indistinguishable, use appropriate definition for the canonical partition function, which at least for internal energy it shows that in both the cases the expression turns out to be same. Internal energy and entropy are connected. This we have discussed earlier also. So therefore, obviously, our next goal should be to discuss entropy. But now we will discuss entropy in terms of canonical partition function. Let us see what is the general expression that turns out to be in such cases. We have derived an expression, or we have connected entropy with the canonical partition function. That was S is equal to U minus U0 by T plus K log Q. We will begin from this. So, when you say monatomic gas, then we need to decide whether we should use q raised to the power n or we should use q raised to the power n by n factorial. That means we need to decide whether the system given to us has distinguishable particles or indistinguishable particles, or distinguishable atoms or indistinguishable atoms. When it is gas, obviously it is not going to be distinguishable, it is indistinguishable. Therefore, we need to use q equal to q raised to the power n over n factorial. This is the expression that we need to use. Let us use that. So, I have S is equal to U minus U0 by T plus K log q raised to the power n over n factorial. Now, let us further expand this. U minus U0 by T plus K log q raised to the power n minus K log n factorial. S is equal to U minus U0 by T plus Nk log Q minus K log n factorial. I can use Stirling approximation n log n minus n. Let us take further U minus U0 by T plus Nk log Q minus Nk log n plus Nk. Remember, Nk is equal to capital N can be small n times Avogadro constant K. That means Nk is equal to, now K times Na is equal to R. R is gas constant. So, I have S is equal to U minus U0 by T plus NR log Q minus NR log N plus NR. We have the expressions in terms of molecular partition function, total number of molecules, and of course we have the gas constant. Now obviously the next step is that we have to now work on U minus U0 by T. You can use U minus U0 in terms of canonical partition function, then convert into molecular partition function, then expand upon that. you can choose that route. Or what I can simply do is, since it is monatomic perfect gas, therefore I can use the result of equipartition theorem. Internal energy of a monatomic gas which is free to move in 3 dimensions. Remember that result was 3/2 nRT. I once again say, we need to find out what we should write in terms of U minus U0 by T. U minus U0, if you go back to previous slide, we have this expression, right, and it is the same expression whether Q is Q raised to the power n or Q is Q raised to the power n by n factorial, and then we can express in terms of molecular partition function and then write the expression for Q and come up with the result. You are still going to get 3/2 nRT. You can do it, or let us for the time being use the result from equipartition theorem. So what do we have now? S is equal to U minus U0 is 3/2 nRT divided by T, because that's what is the first expression, U minus U0 by T plus nR log Q, nR log Q minus nR log n minus nR log n and plus nR. This is what we have now. Okay, let us continue. This is 3/2 nR plus nR log Q minus nR log n, and I have another nR term here. I can combine this 3/2 nR with this nR. So what I have, 3/2 plus 1 is 5/2 nR plus nR log Q minus nR log n. Let us see, can we now convert this 5/2 nR into some logarithmic term? We can do that. So it is going to be nR log exponential 5/2 plus nR log Q minus nR log n, right? So this nR log exponential 5/2 is 5/2 nR. Okay, so S now becomes nR log, what I have is exponential 5/2 Q by n. That is what I have now. Now we need to decide what we should write for Q. This is a partition function, and partition function will depend upon your degrees of freedom. The given system is monatomic gas, perfect gas. Monatomic will have translational degree of freedom. It does not have rotational, it does not have vibrational. Electronic we will discuss later, it's not required here. So that means we need to consider only translational degree of freedom, and translational partition function, you remember, was V upon lambda cube, where lambda was equal to beta h square over 2 pi m let us substitute. So n is a, s is a n r log exponential 5 by 2 v upon lambda cube, v upon lambda cube, and instead of n let me write n times na. The expression that I have now is s is equal to nr log exponential 5 by 2. Instead of q I have written v by lambda cube, instead of n I have written n times Avogadro constant. What I have now is s is equal to nr log exponential 5 by 2 v n Avogadro constant lambda cube, where your lambda is equal to beta h square over 2 pi m raised to the power 1 by 2, or you can write this as h over square root 2 pi m k T. You have expressed beta in terms of temperature. I can now calculate the statistical entropy. To calculate this, what I need is volume what I need is a value of lambda, and if you see here lambda, h is constant, 2 pi is constant, m depends mass of the particle and it will depend upon the temperature. Okay, so you need the mass of the particle and temperature that will decide the value of lambda. So therefore, from the knowledge of translational partition function, now here we are able to get the entropy of the system, provided we know its volume and provided we know its temperature and also the mass. These are the parameters, properties that we require. So we have now been able to obtain an expression from s is equal to u minus u0 by t plus k log q, s is equal to nr log exponential 5 by 2v over number of moles into Avogadro constant into lambda cube, where lambda thermal wavelength we already know is given by beta h square by 2 pi m. This expression is called Secur-Tetrode equation. So remember this equation, Secur-Tetrode equation, which allows you to connect entropy with the volume, with number of moles and with the thermal wavelength. Fine, we have this expression. Now, this expression is in terms of volume, Secur-Tetrode equation. And since we are talking about monatomic gas we assume these are ideal gases. Assuming ideality, let us use the gas law, ideal gas law, and see what shape it takes. If I use PV is equal to nRT, then V upon N is equal to RT upon P. This V upon N I can substitute here, V upon N. So what do we get? This exponential term will become, let me write here only, nr log exponential 5 by 2 V upon N is RT upon P. Then I have Na and then I have lambda cube. Okay. Then R is equal to K times Avogadro constant. This is another equation. That means R upon Na is equal to K. R upon Na is equal to K. So therefore, the new expression that we get is exponential 5 by 2. R upon Na is K, T upon P lambda cube. We have Second tetrode equation. In terms of volume, we have second tetrode equation in terms of pressure. In both the cases, you see lambda is there, temperature term is there. In fact, lambda also depends upon temperature. Second tetrode equation allows you to calculate entropy based upon partition function. And remember, partition function, whether we talk about molecular partition function or we talk about canonical partition function, you can calculate the partition function from the knowledge of energy levels. That means the information that you require is from spectroscopy. Once you have the information about partition function, you are able to then translate that in terms of derivable thermodynamic quantities. Now here we have done, what we have done is, we have simply used Q is equal to V upon lambda cube and then come up with these equations which are basically different forms of the second tetrode equation. One connects entropy with volume, the other connects entropy with pressure. Let us now consider this comment. Second tetrode equation implies that the molar entropy of a perfect gas of a high molar mass is greater than one of the low molar mass. That means the molar entropy of a perfect gas of high molar mass is greater than one of low molar mass under the same conditions. Why? The molar mass that comes into the denominator. High molar mass means lesser thermal wavelength. If lesser thermal wavelength, then the molar entropy is high. And that is what is the comment? That the molar entropy of a perfect gas of high molar mass is greater than one of low molar mass under the same conditions, because the former has more thermally accessible translational states. More thermally accessible translational states, because you have, for high molar mass, you have lesser value of thermal wavelength, and then in order to connect with the thermally accessible states, we need to think about Q translational is equal to V upon lambda cube. If lambda is small, then Qt is more, and if Qt is more, then directly it tells that there are more thermally accessible translational states. Now, if you carefully examine these two expressions, whether entropy expressed in terms of volume or entropy expressed in terms of temperature, lambda is the term, you examine here, is depending upon molar mass and is depending upon temperature. So that means if you fix the temperature, constant temperature means isothermal conditions, then for a given system of a fixed molar mass, then this also becomes constant. Carefully understand that. If you consider an isothermal process where the temperature is constant for a given system, this whole term becomes constant at a given temperature. In that case, the entropy will simply depend upon volume. In other words, it will also depend upon the pressure. So therefore, when you allow the system to change from one state to another state under constant temperature conditions, then you should be able to derive expressions for delta S in terms of changes in volume or in terms of changes in pressure under constant temperature conditions. We will derive such expressions and see how to use that, and also compare the results with the results that we got in classical thermodynamics, but that we will do in the next lecture. Thank you very much.